Okay, as you know, Jordan, although he's grading your lab reports, he is in South America right now with the IRR, so he clearly cannot be doing tutoring. So I have found Brady Darrow, who is willing to do tutoring for you. Here they are. And Brady said that he prefers email, but you can text him. So there's his methods of communication to set up tutoring sessions with him. So he was in the class last year. Don't break things. And I put up some signs. There's one on the door so you can get the information. There's one on my bulletin board, which is just that's way of the door. Okay, getting to the lecture. We are going to pretty much continue from where we were in class on Monday. I lectured for about an hour and 15 minutes in lab yesterday on resistors and resistance and Ohm's law. And so now we have that, but I still need to do a little bit more with capacitors and how we can do some cool things with capacitors before I do more in circuits. So first, the energy stored in a capacitor. If you start with an uncharged capacitor, how much work would be required to move one electron from one side of a capacitor to the other? That is, I have capacitor plates and Q equals 0 for both plates. How much energy is going to be required to move an electron from here to there? What's the change in potential energy for that electron? It's going to be 0 because the change in potential energy is the voltage difference multiplied by the charge. And if they're both a charge of 0, they're both going to be at the same voltage because for a capacitor, we learned that the voltage difference is equal to the electric field times the distance, and the electric field was charge times now I got to think about this. What was it? Those of you in the class where you have to calculate that, the electric field is charge times divided by area epsilon 0, I think it was. I had to stop and think. Feel sad. I think that's correct. So the voltage difference is charge area times epsilon times d. So the voltage difference initially is 0 because the charge is 0. Hence, the change in potential energy moving across is equal to Q delta V would be 0. So it takes no energy to move the first electron across. But once you move the electron across, then you're going to have a charge that's not 0. And then it's going to require energy to move a second electron to join the first. And for each electron you move, it's going to require more and more energy. And so the correct way to calculate the total amount of energy required to move charge across is with calculus. You're integrating. But we're not in a calculus-based class. So what do we do in a non-calculus-based class? We do the integral graphically. We make a graph that shows the voltage difference between the plates. So that delta V is the voltage difference between the plates, which is equal to the charge divided by the capacitance. And then we show how much charge is transferred, and the total work done is the area under that graph. Well, because the line is a straight line with the equation Q over C, then the area under it is the area for a triangle 1/2 base times height. So the area here, which is the total work required, or the change in potential energy as it's charged, is 1/2 the base times the height. So that's going to be 1/2 Q squared over C. So from a graphical integration, we can find that the work required to charge the capacitor, which is equal to the potential energy stored by the capacitor, because we did work to put the energy in, is 1/2 the charge divided by the capacitance, or charge squared divided by capacitance. Now, if you look at my equation here, this isn't the same. And you might say, well, he made a mistake. Hopefully you'd be wrong in that assertion. Let's check and see, though. How can I check to see if these are the same equation? What did you say, Gila? I want to check to see if they're equal to each other. And so what equation can I use that would relate charge and voltage and possibly capacitance? Right. Gila is on top of her game. So we're going to use the equation Q equals VC. And so with the equation I got, potential energy would be 1/2 VC quantity squared over C is 1/2 V squared C squared over C. That's a C. Cancel one of the C's. 1/2 V squared C. That is the same. So those are two different ways of calculating what energy is stored in the capacitor. Now, one more thing that we like to do is to calculate the energy density, the energy per unit volume. And so the energy per unit volume is going to be that potential energy over the volume. For a parallel plate capacitor, area A, separation D, means the volume is the area times the separation. So I can take this and I can calculate that the energy that is stored is going to be one half CV squared over AD. Substitute for physical capacitor. That was our equation for capacitance if it had vacuum in it. If it doesn't have vacuum, it has a kappa. I'm going to go ahead and leave it just for in vacuum. And so then I'm going to have now that's the energy per unit volume, but it has divided by D squared. We don't like that divided by D squared because that D is specific to our capacitor. So the final thing is to once again use the relationship I used before. The voltage difference for the capacitor is equal to the electric field between the plates times D. And so the final coup de grace, 1/2 epsilon 0 electric field times D squared over D squared, 1/2 epsilon 0 times the electric field squared. We use the symbol of a lowercase u for that. That's going to be an important result. That if I have an electric field in a region, there's energy stored in that region, and the energy has an energy density, the energy per unit volume, of 1/2 epsilon 0 times the electric field strength squared. That's going to be an important outcome later on when we get to electromagnetic waves. So I'm pointing it out now because this is where it logically comes in. But we're not going to use it now, we're going to use it later. So we store energy in a capacitor. I started the first introduction of capacitors. I said Capacitors are items that store energy in the form of an electric field. And I said we could also say it store energy in the form of a charge separation. Well, here now we've gotten to that end result of how we have the energy stored in the electric field. Now, just an interesting thing, you've heard the story from the Bible about the children of Israel transporting the Ark of the Covenant back to Israel after the, I think it was the Midianites, but I could be wrong on the people, had captured it and had bad luck and decided that the Ark of the Covenant was bad for them to have and gave it back. And so they're traveling along, and what happens? Bible story. Okay, it starts to rock, and, oh man, my brain is saying us, but I could be wrong. Reaches up to stabilize it. And what happens? He gets struck dead. And then, the Bible goes on to say, it was because they weren't following the instruction of God on how to transport it. It was supposed to be transported with priests carrying it on rods, and instead they had it in a cart being pulled by oxen. Physicists look at that story, and had somebody came up with an idea of how this could happen without God being involved. Now, of course, I believe God is involved, right? But they said, well, that ark was essentially created like a capacitor. The actual technical term for something like this is a Leyden jar, but it had gold foil on it, right? Gold leaf. They make it so it's very thin. And so that gold leaf is a good conductor. And so if you have gold in the outside of the shittim wood and gold in the inside of the shittim wood, and if you don't have something connected between the two, then you could store a charge separation. And because of the attraction between positive and negative, that charge separation just gets stored there, and you build up more and more charge, so it could act like it was a really highly charged capacitor. And if you provide a pathway from one side to the other side, the charge wants to get back. And so if your hand touches, you can have a lot of charge flow through you. Now, of course, the pathway would be from a charge side to the earth, but it's been hypothesized that maybe this was just a natural event with a unintentionally made Leyden jar or special kind of capacitor that had a huge amount of charge stored on it that dumped through the unfortunate gentleman, killing him. So it's kind of an interesting thing to think about these things. Scientists often spend time trying to figure out, how could I explain something that happened in the Bible without God? Because scientists start with a premise that everything we see in nature occurs naturally, meaning without God. And so they don't want to have unexplained things, and so they try to explain away anything that we attribute to God. Okay, let's do a problem or three. Well, it's probably two problems we're going to do. A parallel plate capacitor has plates of this area, 1 meter squared, and separated by 0.5 millimeter. If you think about it, these are ridiculous numbers. A 1 meter squared plate means it's 1 meter by 1 meter. Right? We have plates this big, and they're separated by 0.5 millimeter, which is that amount. Well, that's a millimeter, half of it. About that. That's going to be pretty hard specifications to build. But we're not engineers. We're not making this. We just say we have it. So the insulator has a dielectric constant of 4.9 and dielectric strength of 18 kilovolts per millimeter. What's the dielectric constant telling us? Actually, that's the dielectric strength. The that was where I ended the lecture on Monday, was the table of these. The dielectric constant is telling us about how easily we can polarize the material to counter the electric field that's created. It allows us to make more capacitance in the same area by having a better dielectric. The dielectric strength is what Alex said. That's telling us about how hard it's going to be to have charge pass through. The dielectric strength tells us if we reach an electric field of this magnitude, then we're going to have electricity pass through the dielectric. And if you have electricity pass through the dielectric, it's probably going to damage the dielectric, and so you don't want to reach that voltage. So first, what is the capacitance, and then what's the maximum charge? So let's start with capacitance. We have an equation for the physical construction of a parallel plate capacitor. That's very simple. So I just need to put in my numbers. No units for the dielectric strength or dielectric constant. I told you I get those confused. Epsilon 0, what's the value for epsilon 0? I think it's this. Can somebody check? And then the area divided by the separation. Notice I changed the unit on the separation from millimeters to meters. Did somebody get the dielectric strength formula, or excuse me, the permittivity of free space? And is it 8.85 times 10 minus 12? Okay. So we just put these numbers in our calculator. Somebody else who wasn't looking it up, what do we get when we put these in the calculator?
Times 10 to the negative.
And my units here are going to be, I don't think I ever talked about the units of capacitance. So let's look at what the units are and then see if we can simplify. So meters squared and meters squared, those cancel. And so I have Coulomb squared per Newton meter, or Coulomb squared per joule. And you know what we never write? That. What we write as is farads. I don't even... It's minus 9, not 8. I didn't do the calculation, so I can't vouch for it one way or the other. Okay, we always use the symbol F for farad for the capacitance. So as long as we're using our SI units, we should have, it's in units of farads. So if that's 10 to the minus 9, right, whether it's 10 to the minus 8 or 10 to the minus 9, it's not super important to the lecture. Then I'm going to write this as what abbreviation, what prefix do we use for 10 to the minus 9? Nano. So this capacitance is 8.673 nanofarads. Of course, how many significant digits do I have? 2. So it's 8.7 nanofarads, 2 correct significant digits. So we're able to now calculate the capacitance of this. Nano is small. That was a really big capacitor, and it's a small capacitance. It gives you some idea of the tricks they have to use to make tiny capacitors that have much bigger values. So we found the capacitance. Now, what's the maximum charge that can be stored on this capacitor? Well, we have a maximum dielectric strength of 18 kilovolts per millimeter. That means if I put in an external field of 18 kilovolts per millimeter, it's going to have electric breakdown. Now, with this capacitor, I know that it has a distance of 0.5 millimeters, and the electric field, remember it was V is equal to Ed. The voltage difference between the plates is equal to the electric field times distance. So electric field is voltage over distance. So the voltage I can charge it to, which is just that equation, is going to be the maximum electric field multiplied by the thickness D, which is, I left it in millimeters because I have millimeters and millimeters canceling, and that's going to give me 9,000 volts. So 9,000 volts is the biggest voltage I can put on it before it's going to have electrical breakdown. And then at that voltage, what is the charge? Well, so 9,000 times 8.7, 9 times 9 is 81. So let's just go with 8 times 2 to the 9, 8765. So it's probably not exactly that, but it's going to round to 8. And so we can now find how much charge I can put on this capacitor before it's going to arc. Usually we're paying more attention to the voltage. If you look at a capacitor, it would tell you two numbers. It will tell you the capacitance and the maximum voltage. The reason for the maximum voltage is what we had here, the dielectric strength of the insulator or of the dielectric. And the capacitance is just based on the physical construction. So any questions, and remember this number here is just an approximation. I didn't do the actual calculation. I just said 8.7 is just a little less than 9. It'd be 10% less than 81. Actually, that would be not 10%. Actually, it's 3 out of 9 is 3% less than 81. So it'd be more like 78. It doesn't matter. With a calculator, you could have done that instantly. So any questions about how I did this problem? Is it a reasonable problem? You had to understand physical construction of capacitor and how that gives you the physical capacitance. You had to understand what the dielectric strength is compared to the dielectric constant to be able to do it. And so I think it's a good problem because it requires this knowledge. Now a practical, we're going to have a clicker question on this in just a moment. In one kind of computer keyboard, each key is attached to one plate of a parallel plate capacitor. So what we have here is a parallel plate capacitor. That side's connected to ground, and this side's connected to our computer. And then you press the key. When you press the key, you're going to have, this moves down, so you have a smaller separation. So when you press that key down, you have a smaller separation. What happens to the capacitance? If D gets smaller, what happens to the capacitance? It's going to go up. Now, you have two different things that you could do. You could either have a fixed charge on this capacitor and measure how much the voltage has to change, or you can have a fixed voltage and measure how much charge flows. What they measure is the charge flow. So they keep it with a fixed voltage, and we know Q is equal to VC, and so we can calculate how much charge is going to have to flow. You press that down, D got smaller, so C went up. If C went up and V stays the same, what's going to happen with Q? Q will go up. So that means charge had to come to that key. So if you have something that's holding at constant voltage, suddenly you have charge flowing to the key. What do we call it when charge flows? A current. And so when this has the key depressed, current flows into the key if it's a positive voltage. And then when you let go of the key, current flows out. And so that's how this key works, is it measures the current flowing in or out to tell if it's been depressed and if it's been released. Okay, so clicker question to see if you followed along. When a capacitive computer key is depressed, what happens to the charge in the capacitor if voltage is held constant? Okay, Michaela, Ashley, and Rebecca. Just Ashley.
I'm on the wrong channel.
Well, I have 3 clicker questions. I can't guarantee. So there we go. So we had 4, 14, and 2. Okay. The lucky winner for this question is Alex. Alex, which one would happen, and give us an explanation of why?
I said A, but I'm guessing I was wrong. So we're saying that the voltage, it seems to me like the charge would decrease because the capacitor would be discharging. Right?
Okay. It goes the other way. When you press down on the key,
Oh, it's charging it.
the capacitance goes to a higher value.
Oh.
And so you have to charge it because Q is C delta V. If V goes up, then Q has to go up. So when you press that button, the charge on the key has to increase. Now we talked about resistors in series and parallel. Now we're going to talk about capacitors in series and parallel. And we start with capacitors in series. If I put capacitors in series, let's start by imagining that we were not connected. So we're not connected to the battery, and we have charges of 0 on each capacitor. So we start with everything uncharged. And then we connect the wires to the battery. If I connect the wires to the battery, what's going to happen to electrons? Where will electrons be collected by the battery? Which terminal, positive or negative, is going to attract electrons? Okay, positive. So we're going to have electrons travel to the positive of the battery. We learned about batteries yesterday. Do batteries store these electrons? The answer is a straight no. They don't store charge. The batteries give energy to charge. They don't store it. So those electrons don't stay in the battery. They have to come on out. So those electrons come out and they end up there. Now, we have the capacitors in between. We don't have any place for these electrons to go. Any electron that leaves the top of the first one ends up at the bottom of the last one. So what's going on in between? What's going to happen to this plate right here? The lower plate right here. If you have extra negative charge below it, what's that going to do to the electrons on that plate? It's going to repel them, push them away. So the electrons are going to leave this plate and go up to this plate. So the electrons move up to that plate. So that's going to now make this plate was negative. That made the upper one positive with this one negative. This one that lost electrons was positive. That sequence is going to occur again for the next set. So we're going to have electrons move like that, making it again positive and negative. But if you look at those, the electrons left one capacitor and moved to another one. So the charge, the positive charge, based on the electrons that left, has to be equal in magnitude to the negative charge in the next one where the electrons went. And the same is true for the electrons that went through the battery. So in the end, every single one, and I now have to erase where I obliterated the stuff, every single one of these plates has the same magnitude charge. It's positive on one side, negative on the other. So fundamental outcome from this, when you have capacitors in series, what's the same for every capacitor? Same what? Say louder. Charge. So now we want to find an equivalent capacitor to these three capacitors that are arranged in series. And so the relationships I'm going to use are this fact that they have to have the same charge on each capacitor and that Q is equal to VC. So I look at this here and I say, well, they all have the same charge, so I'm going to have V1 is Q over C1, V2 is Q over C2, V3 is Q over C3. Just applying that rule. And over here, V total is equal to Q over CS. If this capacitor is exactly equivalent to the three, then it's going to have the same charge transferred to it and the same voltage. So now I look and I say, same battery means that the total voltage needs to be the same. We saw yesterday the voltage is just add. Well, you may have seen depending on your test. But the voltage just add. And so I should have here voltage total is equal to V1 plus V2 plus V3. So that's going to be Q over C1 plus Q over C2 plus Q over C3. But from the right-hand side, that should equal to Q over C series. The last step, of course, is divide everything by Q since every term has a Q. And you get the relationship that 1 over C series is equal to 1 over C1 plus 1 over C2 plus 1 over C3. Is that the way it was with resistors? It's not, but it looks familiar. With resistors, when we added resistors in parallel, it behaved this way. So with capacitors, when you add capacitors in series, what's going to happen to your total capacitance? It's going to go down. Less is what you said, right? So the total capacitance is going to go down when you add capacitors in series. Why would it go down? Because we are able to store, remember, capacitance is the voltage, or Q is the charge per voltage, and we're able to have a bigger voltage with the same charge if we have capacitors in series. What if they're in parallel? What do you think you're going to get for the outcome when they're in parallel? Well, it tells you in this diagram what you're going to get for the outcome. And the reason is this one doesn't even go through and do it carefully. It does it very logically. Capacitors, the capacitance is some constant times the area divided by the separation. If I put capacitors in parallel, then effectively I've taken the total areas, area of capacitor 1 plus area of capacitor 2 plus area of capacitor 3. And if they all have the same separation initially, so this is specific to having the same separation, then the total capacitance when they're in parallel is just going to be epsilon 0 times the sum of the areas divided by separation, which is exactly what you get if you just add C1 plus C2 plus C3. So this picture is just doing the work by saying you put them in parallel, the area increases additively, so the capacitance should increase additively. But of course, that was assuming the same separation. So we should be more careful. If we're going to be more careful, we have Q equals Q1 plus Q2 plus Q3. If they are in parallel, they all have to have the same voltage. So we're going to have, this is equal to VC1 plus VC2 plus VC3. Come down to this one, Q is equal to VC parallel. So we set Q equals Q. We have VC1 plus VC2 plus VC3 equals VCP. Divide out all of the V's, and you get C1 plus C. That's a C. And there we have the rigorous proof. It wasn't very hard to do the rigorous proof. All I had to do was say that the total charge is the charge on each one, and the voltages are the same, and boom, it just fell out of it. So there's rules on how capacitors work. We've talked about what happens to the charge if you change the capacitance. We've talked about how multiple capacitors can combine. In real circuits, capacitors are used for their energy storage properties. In an alternating current circuit, we'll learn how that applies. In a defibrillator, you charge a capacitor. That capacitor is storing a lot of energy. Remember when I talked about the defibrillator, I said some of them talk about it as the voltage, and some of them talk about it as the energy. Well, now we've seen what the energy relationship is for a capacitor and voltage. That is, the energy is 1/2 CV squared. So talking about the voltage tells you about the energy, just like talking about the energy. So there is a square, they're not a linear relationship, but you're talking about the same ideas. We've already talked about the battery. And then I said in lab yesterday I would work this problem in class today. This problem is asking, what is the current flowing through this circuit? So, and what's the voltage across this resistor? So I need to find currents and voltage. And when you look at this, there are two possible responses. One, it's like fight or flight. Flight is, oh no, I can't possibly do this, run away. And the other response is, well, what do I know? So if I try to solve this circuit, we really only have one equation so far. So we're going to have to use that one equation, two others that involve resistance. But that one fundamental equation is Ohm's law. So we're going to rely heavily on Ohm's law because it's all we really know. But we do have another thing, how resistors add in series and parallel. So we can't just apply Ohm's law right off the bat. We don't have enough information. But we can start combining resistors. So what's the first thing you would do in trying to simplify this circuit? Do what? Okay, take the two resistors, name the two. They have numbers, so which two?
R2.
Okay, just making sure we're clear on which two. Take R2 and R3 and combine them because they are connected in either series or parallel. And Alex might have said which one. How do you determine if it's series or parallel? The tops of both of those resistors are connected together. The bottoms of both the resistors are connected together. That's how you identify parallel. There's no other pathway, no other options. You have just those. So we have 1 over R parallel is equal to 1 over R2 plus 1 over R3. So all I got to do is do my calculation. A lot of people have learned this equation inverted. That is, R parallel if you have only two resistors, that equation works. A lot of people just learn this and don't realize that doesn't work if you have three resistors. It only works with two. If you have three, you're going to have, you're going to have R2, R3 plus R1, R3 plus R1, R2, all divided by R1 plus R2 plus R3. And it gets more and more complicated as you add them. Because this here is always the correct form, and then it's doing the inversion that makes life hard. But in this case, it's going to be easy enough to say, well, 6 times 13 is 78, and 6 plus 13 is 19. And so 78 divided by 19 is somewhere on the order of if it was 20, it would have been 40 and 20. So it's going to be somewhere close to 4. What is the actual value, somebody? 4.1? So we have 4.1 ohms. And since we have 3 sig figs, let's get 4 digits there so we have one more than the sig figs. So what is the... Okay, that way we're not going to lose information in our rounding. So 4.105, so now we can rewrite the circuit as now notice I put a battery here because nobody makes a 12-volt cell like the picture shows. Right there, I don't think there's a chemical reaction that will produce a 12-volt cell. And so I changed it to the symbol for a battery. Technically, what's the next step? I say technically because I would never do it. We have two resistors. We had combined them into one series resistor. We'd combine this into when they're in series, you just add them, so that'd be 5.105 ohms, 12.0 volts. Now we can calculate the current using Ohm's law. So now we first apply Ohm's law. I is equal to V over R. So there's 12 volts across there because the battery is straight across this. And so the current is a little bit more than 2. What do we get with 12 divided by 5.105? 2.25? 3.5. And can you give me just one more digit?
1, because it's not.
So we have 2.351 amps flowing through that resistor. Now coming back to what we want to know what that current was. We just found it. We want to know this voltage. How do I find the voltage across the 1 ohm resistor? If I have, wrong one. If I have 2.351 amps flowing out of the battery, come back to my original position or equation, I now have found that current. That's the current going through this resistor. So the voltage is going to be 1 ohm times 2.351 amps is 2.351 volts. Which side is positive for this resistor? I heard top and bottom, but it's left to right, so it couldn't have been either of those.
Left.
Okay, left is the positive because we lose energy as the current flows through. And so we're talking about a mythical positive current, but that mythical positive current is losing energy. So it was positive on the side where the current entered and negative on the side where it exited. Now we started with 12 volts. We went down 2.351 volts. So what remains over here is the total minus V1. So that's going to be 12 minus 2.35 is 9.649 volts. And now that I know this voltage, I can find the current going here by again applying Ohm's law. I2 is equal to V parallel over R2. And so it's a, what, 1.6? 1.66? Somebody? What is it actually? Okay. I was off with my last digit by a place. So there we found all of the values. That's how we're going to solve circuit problems today. By the time we get to lab next Tuesday, we're going to have Kirchhoff's laws and a new method for solving the circuit problems that allows us to do more sophisticated problems than these will allow for. Because sometimes resistors are neither in series nor in parallel. You can't use this method if the resistors are neither series nor parallel. So next class period, we'll get some examples of how that can occur and how to treat those.